Okay, so I'm going to get started. So today's announcements, the Chapter 1 sapling. I didn't quite finish Chapter 1 last Friday, so I'm going to wrap it up today. So the due date for Chapter 1 on sapling I will change to Monday next week, 1 week from today at 9 a.m., which is the time that all the saplings are going to be due, that time in the morning. Also, recitations start today, so make sure you go. There's no quiz this week, but there will be next week in recitation. And then if you have exam accommodations, I'm starting to plan out how that's going to look. So please get me your accommodations letters sooner rather than later so I can sort of tie you into the planning and figure out a time that works for everybody who's involved. Okay, questions about those? Okay, cool. So I sort of mentioned last lecture that I might skip the last part of Chapter 1. On Friday after lecture, I went through Chapter 2 and 3. And it looks like, no, I'm not going to be able to do that because I sort of tie in some stuff in those chapters to things that I cover in the last little bit of Chapter 1. So I think all of today's lecture is going to be the last part of Chapter 1 and maybe a little bit of Chapter 2 at the end. And then that'll still give us 3 lectures for Chapter 2, which is a shorter chapter, and 3 for Chapter 3. So you should be good. Okay. So where we left off last time is looking at atomic orbitals. And so we looked at the quantum numbers that determine the properties of the orbital. So the relative energy level, what shape it is, like S, P, D, and then sort of how many of each of those types of orbitals there are. And then we looked at filling electrons into those orbitals. So let me do one more example that's in the notes that I didn't get time to do last time. So the AO diagram for fluorine, which according to the periodic table has an atomic number of 9, so should have 9 electrons if it's neutral. Okay, so we're only going up to sort of the 3 principal quantum number orbitals, so 3p, 3s. So I'm not bothering to get up into the d orbitals where things start getting sort of like, it's not all just the 1s together and the 2s together and the 3s together, but for our purposes, we're not going to get high up in the periodic table that we need to worry about that complication just yet. So, okay, so for those of you who missed lecture, this axis is increasing energy. So we've got the 1s orbital. It's got the lowest principal quantum number. It's lowest in energy. And then we've got everything with a principal quantum number of 2 is higher in energy. S is slightly below P, but not by as big a gap as from 1 to 2. And then the 3s are above that. And I'm drawing 3 dashes for the P's because if you remember, we have 3 P orbitals all at the same level. So I don't think I use this term in the notes, but these are degenerate orbitals. They're all at the same energy as each other. Okay, so when we start filling in electrons, we've got 2 things to sort of guide us there. One is that we start from the bottom and build up. That's the Aufbau principle. And then the other is, if we get to a place where we have orbitals at the same energy level, we use Hund's rule to fill them. So we go through, we put 1 electron into each orbital first, all pointing the same direction. And then if we still have leftovers, we can go in and put a second electron pointing the other way. So when we're showing electrons in here, we can use either an up arrow or a down arrow because there's 2 spins that we can have on the electrons. So that's kind of how we're showing them here. So if I start filling in 9 electrons, I do 1, 2 for the first orbital, 3, 4 in the second orbital. Now I need to use Hund's rule to go across, so I can do 5, 6, 7, and now I can start filling back in 8 and 9. So that's how the orbital filling would look for an isolated neutral fluorine atom by itself. So we can write out the configuration on this as 1s2 electrons, 2s, 2 electrons, 2p, 5 electrons. Okay, so that's kind of a refresher of the end of last lecture. Any questions about that? Yeah?
What is the purpose of adding in extra energy levels that aren't going to be built into
None really. I'm just, yeah, showing that it keeps going above that. And if I really wanted to be pedantic, I could just like fill in up to, I guess, infinite quantum number, although at some point like it becomes irrelevant because the nucleus is never going to get big enough that it's allowed to have that many electrons and be neutral.
And one more question. Is the energy jump between 1s and 2s the same as 2s and 3s?
No, good question. So I'm being really vague as to like the actual scaling here, but this is actually quite a bigger jump than this one to this one. So, yep. Okay. And really, the ones within the same energy level should probably be a little bit closer together. I just sort of like did the ordering without worrying too much about spacing. Okay. So I sort of mentioned this is for an isolated atom. So if a single atom of fluorine is floating around in interstellar space by itself, this is how it's going to end up holding its electrons. But chemistry would be extremely boring if that were all we were looking at as individual atoms with no interaction with other things. So what ends up being a lot more relevant is what atoms do when they're around other atoms. So it turns out that what atoms can do is actually mix orbitals together or hybridize them, because it turns out to be an energy benefit as far as bonding goes. So what we're going to look at now is hybrid orbitals. So these are still on a single atom. But it's more, an atom can sort of average some of its orbitals together to get what ends up being better overlap when it tries to do covalent bonding. Okay. So this actually does cost energy, a little bit of energy up front, because you are actually ultimately putting electrons into slightly higher energy positions than they would otherwise be. But it turns out that it's more than paid for by the fact that you can get better covalent overlap and get energy back out of it that way. Okay, so we're going to name our hybrid orbitals after what we're averaging together. Okay. So for example, we could average together a 2s orbital plus 3 of our 2p orbitals. And if we do that, we're going to get a total of 4 new orbitals. So this is kind of an important point to mention, is that the number of orbitals is conserved. 3 orbitals in gives you 3 orbitals out. 4 orbitals in this case, gives you 4 out. So we're going to get 4 of some new hybrid orbital, and we're going to call it sp3. We're calling it that because there's a single s orbital, and there's 3 of the p orbitals that we're averaging together to make that happen. Okay. So the shape of these orbitals, explaining where they come from basically comes down to like 3-dimensional calculus, unfortunately. But it turns out that the shape of these sp3 orbitals are going to look like, so they have some what's called S character and some P character. They look like lopsided dumbbells. So we're going to get 4 of them. And they have one big lobe and one small lobe. And the orientation actually turns out to be sort of one pointing straight up, one down to the right, one down to the left, and then one, the hardest to draw, is sort of coming straight out at you. I guess I can tilt it a little bit so you can see the tiny lobe in the back. Okay. So it turns out just by doing a sort of combination of the function for the s orbital and all 3 of the p orbitals, you actually end up generating 4 new orbitals that happen to point out at the corners of a tetrahedron. So you actually get tetrahedral geometry out of it this way. And again, we're not going to get into like how that's actually getting derived, unfortunately, but it is pretty interesting if you get a chance to take PChem in the future. Okay, so this is actually sort of where we're getting the tetrahedral geometry from on a carbon with 4 bonds, because I guess there was nothing about the p geometry orbital, the geometry of the p orbitals that was inherently tetrahedral, but it turns out the sp3 geometry is actually tetrahedral on carbon. So sp3 geometry is tetrahedral. sp2, where we're combining an s and 2 p orbitals, happens to be trigonal planar. And sp, where we're combining an s and just 1 p orbital, happens to be linear. Okay, so we can actually go through and show, I'm actually going to scooch this down just a little bit, sorry. Trying to plan for board layout is like an extra layer of work on top of explaining stuff. Okay, so sp is linear, and then I can do another column for no hybridization. Okay. So what I'm going to do is focus on the part of the atomic orbital diagram that just has like the 2p and the 2s, because that's going to be most relevant for what we're doing with, say, a carbon atom. So if we do no hybridization, it's exactly the same as what I've shown up here, 2p and then 2s. And I'm going to spread these out just a little bit from what I have up there, kind of zoom in on it height-wise so we can get a better look at what's going on with the energy levels. So pretty much like an atom floating around by itself in space keeps its p orbitals and its s orbitals completely separate. They're at whatever the default energy is for those levels. If it turns out to be beneficial to the atom, we'll go into when that's the case, then we're going to blend together 1p and the s orbital. So maybe we're going to average those together. And what we're going to do, so like 2 of the 2p orbitals stay completely untouched. Those are not getting hybridized. But these 2 orbitals that we're averaging together, one of the p's and the s orbital, are going to form something that's about the average of the energy levels for those 2 orbitals. So these ones we would call sp, because we're merging together 1s and 1p. Okay, so that's kind of what's going on with the energy levels. If I want, I can sort of do the same thing for the s and 2 of the p's. So like average together this guy and 2 of these guys. Again, one of them would stay where it is because we're not mingling it with anything. But the other 2 would go at an energy level that's kind of like a weighted average of the 3 that we're merging together. So these would be sp2 orbitals. Or I can just average everything together overall, all 3 of the p's and the s, and get something that's has all 4 equivalent sp3 orbitals. Okay. So when we're looking at the new hybrid orbital, we can actually figure out like what the properties of it are going to be like. And this has to do with things like energy and geometry, things like that. So the way we describe these is because they're made up of a single s and 3 p orbitals, these have 25% we would call s character. So whatever property we're looking at, it's going to be about 25% weighting for whatever s had, and then 75% p character. Over here, our new hybrid orbitals are sp2. So s is making up a third of that, so we'd expect to see 33% s character. And 67% about p character. SP is 1 of each, so it's half and half, 50% and 50%. Okay. So in general, we can get a pretty good idea of the properties of our new hybrid orbital just by sort of averaging together whatever like the energy levels for the parent orbitals, we'd call them, are. Okay, so questions about that before we look at how to apply these? Yeah. Yeah, good question. So I guess as far as we're concerned, yeah, we're only going to be doing this in the valence shell. There is like some evidence to show that it can happen in like a layer or 2 below that, but it's kind of chemically irrelevant, so it ends up not being super important for bonding. So, uh-huh.
How do you know what kind of hybridization?
Excellent question. So that's actually what I'm going to cover right now. Yep. Okay. Any other questions about sort of the energy diagrams before we move on? Yeah.
How do you determine the percentages?
Oh, so it's pretty much, this one is just straight up 1s and 1p, so it's 50% of the total is s and 50% is p. Yeah, so it really is just as simple as it looks. Yeah. Okay. So in terms of how to tell what hybridization you have on an atom, we can actually tie this back into Vesper theory from a couple lectures back. So, and I guess the geometry up here is kind of a tip-off that they might be related to each other. So the total number of hybrid orbitals on an atom should be equivalent to the number of groups attached to it under Vesper theory. Okay. So in other words, an atom with 4 groups should be sp3 hybridized. So for example, you know what, I'm just realizing this example that I have in my notes introduces sort of a shorthand thing that I haven't talked about yet and won't until next chapter. So I'm just going to go with H's for now, but okay. So for example, if we're looking at this carbon atom, under Vesper it's got 4 groups. So Vesper says it should be tetrahedral. And so we can pretty much use that in the absence of any other information to sort of work backwards and say, okay, it's tetrahedral, therefore it should be sp3 geometry. So this is an sp3 hybridized carbon, we would say. Okay, so another example, we'll just do one for each geometry on carbon. So if we're looking at this one, Vesper says 3 groups. So trigonal planar, which tells us that it should be sp2 geometry on there. Okay, so what this means, we know that sp2 means that we have one unhybridized p orbital left over. Sorry, I'll get to you in just a second. So it's sp2, but with one leftover p orbital. And that is actually going to be quite important in just a second here in terms of what we can actually do with that leftover p orbital. Okay, sorry, was that your question?
These shapes that you're naming are just for the electron geometry, right?
Right, yeah, I guess in this case it turns out to be the same thing because we don't have any lone pairs on there. But yeah, the electronic geometry is kind of what we're going off of. Yep. Mm-hmm. Okay. So then sort of the third option here is 2 groups. So it's linear or SP geometry. So because the carbon is using up one of its s, or its only s, and one of its p orbitals, that tells you it's got 2 leftover p orbitals that it can do something with. Okay. So any questions about that? Okay, cool. So the reason that board is not going to stay up. All right. The reason that we're looking at leftover orbitals here is because the next thing that we're going to do, so we've looked at atomic orbitals on an isolated atom. We've looked at hybridized orbitals on a single atom when we know it's around others. But what we can look at now is combining orbitals across multiple atoms when we start forming covalent bonds between them. So this is molecular orbitals. So it's sort of the third layer of theory here. So molecular orbitals, or MO theory, as it's more commonly referred to. So what we're going to do here is start combining orbitals on multiple atoms because we know that electrons have to exist in orbitals, and we know that we're sharing electrons between atoms when we make a covalent bond. So it makes sense that if we want to put electrons around 2 atoms at once, we'd have to make some sort of new orbital, like a molecular orbital between those atoms to throw the electrons into. So that's what we're going to look at doing, is how to build some sort of shared orbital between 2 atoms to make a molecule. Okay, so I'm going to sort of cover the rules of the game for making MOs, and then we can go through an example of how to do this. Okay, so to do MO diagrams, so we're going to show the 2 atoms that we're bringing together in the left and the right column of the diagram. And then in the middle is the new MOs that they're going to give rise to together. Okay, so we sort of have an idea of what the atomic orbitals are going to look like already, because that's kind of told to us by the hybridization that we already know that we have. So we're going to start combining them to get our new MOs. So again, number of orbitals is conserved. So 2 orbitals in should give you 2 orbitals out. Orbitals can combine with either constructive or destructive interference. So constructive, I guess if you have 2 standing waves and you overlap them so that the peaks sort of match up with each other, they add together. And the equivalent for our atomic orbitals combining is same color overlap. So like 2 dark colored lobes overlapping or 2 light colored lobes overlapping. Or they can have destructive, where you sort of subtract them from one another. So like if on like a guitar string wave, for example, like if the peak of one wave overlapped with the trough of another, they'd sort of cancel each other out there. So they'd have to be opposite phase, or in other words, different colors. Okay, so this is called constructive interference or destructive interference. Okay, so you're actually going to have, for a given pair of AOs coming together, you've got 2 different ways they can overlap. One is going to be constructive, one's going to be destructive. And that's actually how you get the 2 new orbitals from combining 2 atomic orbitals, like one good overlap and one bad overlap option. Okay. It's also worth noting that destructive creates a new orbital with more nodes. And I see your question in the back. I'll get to you in just a second. Okay, question?
Well, what do you mean by the phases that are canceling out?
So it might make more sense when I start going through an example, but if you're okay with that, I might finish like writing this out first. Okay, cool. Okay. So next up is looking at what type of overlap we can get. So head-on overlap creates sigma orbitals, and side-on creates pi. And again, I'll show how that looks in a second here. So this one is usually less overlap and less energy change. Okay. And then so as a general rule, more nodes is going to be higher energy. And then as far as labeling, bonding orbitals are lower in energy than their parent AOs. And so those we're just going to label as straight up like sigma or pi orbitals, depending on which one of those types of overlap we have. Anti-bonding are higher in energy than the parent AOs. And so those we're going to label as sigma star or pi star. Okay. So again, this is a whole lot of mumbo jumbo right now. Once we start applying this in an example, it'll make more sense. But just a couple more things that we got to talk about here before we get going. Once we got our MOs generated, then we can start filling them in exactly the same way that we did for our atomic orbitals. So like Aufbau principle, Hund's rule. And then the bonding order, we already looked at that a little bit, is like how many bonds there are between two atoms. But we can also figure out what that is from the MO diagram. So bond order, according to the MO diagram at least, is going to be number of electrons in bonding orbitals minus number of electrons in antibonding divided by 2. Okay, so let's actually start doing something with this. I think, yeah, I have room down here. Okay, so let's do an MO diagram for the simplest molecule we could possibly come up with, H2, hydrogen gas. So we're going to do 3 columns here, a single H atom on the right, a single H atom on the left, and the H2 molecule that they make gets generated in the middle here. Okay, so what atomic orbital am I looking at for each of those atoms? 1s, right? Nice. Okay, so 1s here, 1s there. If you want, you can show sort of the electrons in each of those orbitals. Spin doesn't really have anything to do with each other because for now they're just 2 isolated atoms when we're showing them on the right and the left. Question or stretch? I think that was a stretch, sorry. Okay. Okay, so what we're going to do is, and it might actually help if I show the shapes of the orbitals. So we've got 1s orbital, a little sphere around an atom, and another 1s orbital. And I'm just arbitrarily, for this version, going to show them being the same color. Maybe I picked to have them both shaded. So if I bring them together and I happen to be showing them as the same phase, the same color, they're going to get, what, constructive or destructive interference? Constructive, yeah. And so you can sort of think of it as these 2 packets of like electron density or wave function are going to sort of merge together when we get the atoms close together. And they're going to form sort of this egg-shaped or oval-shaped packet around both nuclei. Okay, so that was constructive interference. The other option is, because there's no correlation when we're looking at individual atoms, like I could just arbitrarily choose to show one like dark colored or light colored and the same for the other. So I could just as easily have chosen to show them out of phase or mismatched in color when I bring them together. And both of these are like possible options, which means that both of them are going to be happening, and they're going to give rise to 2 separate new orbitals by doing this. So it's not like an either or, it's like both of these combinations are happening at once. Okay, so I do a mismatched color overlap, which gives me destructive interference. And the way that looks is they sort of cancel each other out in the middle. And so you get sort of a new node cutting down between them. And then like the sphere sort of gets distorted to the outside of the nuclei pair. So like that. So that's a new node. And that makes sense, right? Like we always saw before when we're looking at atomic orbitals that a node is any place where you can cross over and go from light to dark or dark to light. So that's kind of what we're creating when we bring them together out of phase like this. Okay. So we know that more nodes means higher energy. So top or bottom, which one of these is higher energy? Bottom, right? Yeah. So this is higher energy. This happens to be an example of head-on overlap. I'm sort of like pointing the closest parts of the two orbitals directly towards each other, which is actually the only type of overlap I can ever get with s orbitals because there's no bits sticking out to the side. So these ones I'm going to call either sigma or sigma star. They're both sigma type orbitals. I know that this one is lower in energy because it's got fewer nodes. So this one I'm going to call sigma. And this one, this whole orbital with its two lobes or its two parts, I'm going to call sigma star. Okay, so when I start drawing in the child or the offspring MOs from their parent atomic orbitals that I built them from, one of them is going to be higher in energy and one's going to be lower in energy. And I know sigma star is going to be higher because it's got that extra node, and sigma is going to be lower. And traditionally, this is like the simplest possible version of this, but sometimes it gets hard to keep track of what's coming from which parents. And so a lot of the time, people will show these little dotted lines to say like this 1s orbital gave rise to that sigma star and that sigma. And the same over here. This is a parent to this one and this one. Not super necessary here, but can sometimes be useful for keeping track. Okay, so we've got a sigma orbital that's this egg-shaped thing that's lower in energy, and we've got a sigma star that's higher in energy. And we've got a total of 2 electrons now in the whole newly built system here in the middle to fill them into. So we're just going to start filling in by Aufbau principle. So we got 2 electrons. We can do 1 up, 1 down. I happen to show them as 1 up and 1 down on the sides, but really it totally doesn't matter. It's when they're isolated atoms, they can't talk to each other. Just so long as you put them in with the right spin once you start doing the molecule. Okay, so looking at this, what we've actually accomplished is we had 2 electrons that were at some set level of energy in a 1s orbital. And we've created a new place for them to hang out that's actually lower in energy than either of the atomic orbitals where they were before. So that's kind of why this is beneficial to the atoms, is it's actually giving both the electrons like a lower energy position to be in, which is why the covalent bond is actually favorable to form. So you can sort of explain covalent bonding in terms of like it wants a full octet, or you can explain it by this MO model that sort of looks at energy levels for electrons and sort of come at it that way. Okay, so questions about that? Yeah? Hmm?
So is that kind of diagram going to be pretty much, or pretty similar to all like the diatomic elements because that's why they want to be?
Yes, but once you start bringing in pi bonds, then it starts getting more complicated, so I'm going to do one of those as well. So good question, thank you. Okay, so I didn't leave myself enough room. I'm going to erase the board over there, and then, sorry, question real quick.
Yeah. Is the sigma star,
Mm-hmm.
is that just for us to know that we chose the lower energy? Is that just for us?
Excellent question. So it turns out that when we start doing reactions with molecules, a lot of the time when we're breaking a covalent bond, it's because more electrons are coming in, and the only place for them to go in the molecule is into the sigma star. And then based on the bond order, which I'm going to calculate over here in a second, that tells us the bond order goes to 0, and so the bond has to break to accommodate that. So you can actually, like, even though it's not being used like when the molecule is sitting around by itself, it does turn out to be sort of a vulnerable point of attack, I guess, for incoming electrons, and that's actually what's driving a lot of chemistry. So give me 1 second here, and I'll work through an example of that. Okay. So one last thing to look at that we haven't done for this diagram yet is looking at the bond order, guys. So for this one, just to wrap it up, the bond order is going to be 2 electrons in a bonding orbital minus 0 electrons in antibonding all over 2 gives us a bond order of 1. So we could have figured that out just by drawing the by drawing the Lewis dot diagram for a hydrogen gas. So we already know that this has a bond order of 1. So you might be thinking that was an awful lot of extra work to go to just to get the same answer that we could have gotten just from drawing dots. Why bother doing the MO diagram? 2 reasons. One is MO diagrams actually let us cover a lot of weird examples that we don't really have any way to explain with Lewis dot diagrams. So we can do like odd numbers of electrons, which I'm going to do as the next example, and a few other weird things. And also, this gives us more information about the shape of those orbitals, which turns out to be crucial for understanding some reactions later on. Okay, so let's do sort of a quick variation on this H molecule real quick. So how about H2 with a negative charge? This is pretty unstable, but it turns out we can still draw an MO diagram for it. So again, we're going to do 3 columns. If we split it up, we might want to do it as like an isolated H atom that's neutral with 1 electron, and maybe an H minus ion where it's picked up an extra electron. So it's got an up electron and a down electron in it. So a hydride anion. Again, we can generate the orbitals exactly the same way. It looks exactly the same. But now when we go filling it in, we still got the same sigma and sigma star, but we got 3 electrons to plug in there total. So we've got 1, 2, and then 3 here. All right, so the shape of the orbitals is going to be the same, but we've got an extra electron, and the only place for it to go is into this antibonding orbital. So the bond order of this is going to be now 2 minus 1 over 2 is a half. So this is not something we had any way to cover with Lewis dot diagrams, a half of a bond. But it turns out MO diagrams are flexible enough that we can actually look at cases like this. Okay. So one more example to walk through before we're done with the chapter is we haven't really looked at pi bonds at all. So pi bonds are I guess actually before I say that, so sigma bonds, the first bond between any 2 atoms is a sigma bond. And then all subsequent bonds are pi. So how that looks, if you've got like a C-C bond here, one of those is going to be sigma, and the other, and it doesn't matter which you pick, is going to be pi. So these 2 have a sigma bond and a pi bond. If you got C triple bond C, this is going to be 1 sigma and 2 pi bonds. Okay. So it's pretty much like the first bond between the carbons is sigma, and then any additional bonds are going to be pi. Okay, so pi bonds are side-on overlap. And those are going to form between the leftover p orbitals that we didn't end up hybridizing together. So if we have, say, an sp2 carbon and an sp2 carbon here, both of them have this leftover p orbital that's sort of stuck above and below the plane. And those can kind of either do constructive interference, where they sort of blend together over the top and the bottom, and make this p orbital here. Okay, and that's a pi bond, that's side-on overlap. Or they can do destructive interference, or if you get the color mismatched, like one's dark up and one's dark down, they'll sort of push away from each other, the same as when you tried to do sigma with a mismatch. So that has an extra node that you made, which makes it pi star. Okay, so I don't think I'm going to have time to draw the entire MO diagram for this. I think I'm going to just wrap it up here for this chapter. We are going to revisit these when we start looking at pi bonds and alkenes in chapter 4. So I may just sort of tie it back in there. But that's kind of what that looks like if you're curious.